Okay, so in this video I wanted to just give you an example of how to use Simulink to run a simulation of a closed-loop system. So what I did was I opened MATLAB and then I clicked on this little button here to start Simulink, and that opened up the Simulink library browser over here. And then I clicked on this little white page, and that gave me an untitled workspace that I could start making my simulation in. And you see over here in the library browser I have commonly used block and continuous. I'm also going to use sources and sinks. So continuous, what I want to do is I want to create a transfer function. So we need a transfer function here. I just dragged it over, and to be a little bit like the example that I did, so if you look here, I got numerator coefficients, denominator coefficients. So what I'm going to do is I'm going to leave the numerator as 1, but I'm going to make the denominator appropriate for s plus 2. So we got s and 2 here. Okay, this is the s to the first power and the s to the 0th power. And so now you see it changed the transfer function, so it says 1 over s plus 2. And now what I'm going to do is I'm going to add a source here because I want to make a step function. So I go over into the sources, and then if I scroll down here, there's step is one of the sources that I can have. So that's going to be my input to the system. And then the output I'm going to display on a sink here. And the sink that I'm going to use is a scope. So I'm going to come over here and make a scope. Okay, and then I can connect these things together, and MATLAB has a tricky way to do this by just control. It will automatically put things together, and I can do the same thing with the step here, like that. Okay. Oh, what happened there? Eventually drag this thing over into that. There we go. Okay, and so now I have my simulation. And it's this little 10 here is telling me how many seconds the thing is going to run for. It's the simulation stop time. And I can press play to run this thing. And I can just use it as it is. And one thing that I want you to know, so if you remember, this is like we always talk about 1 over s plus a. And the Laplace transform for that is e to the minus at. Or the time constant is 1 over a. So in this case, the time constant is 1/2. So 1/2 second time constant. And so if you remember, settling time is about 4 time constants. And so with a 1/2 second time constant, basically everything is going to happen within about 2 seconds. So I'm going to change this to 3-second simulation. And then we'll run it. And there it goes. And if you notice, MATLAB threw an error here. It says using default value for maximum step size and blah, blah, blah. And so you could go into the simulation and you can go into the configuration parameters and you can fix it so that it won't do that anymore. It actually turns out to be not to be very important here because 0.06 is a lot smaller than the time constant here, and so this is a perfectly fine maximum step size. So now it's telling me, okay, simulation start time, stop time. It's using a variable step solver and maximum step size. I'm just going to enter in a thing so it stops giving me that error message, 0.05. That's a pretty fine step size because if you think about it, right, if my time constant is 2.5 or is 1/2 second, that would be 0.5. So I've got it about 10 times smaller than the time constant. So that's a reasonable choice there. Okay, and I do OK, and now I can run it and it won't give me that error anymore. Now I double click on the scope to display the result, and bring it over here. Auto scale. If I right click it, it'll auto scale. Okay, there we go. And so it's starting at 1 second and it's going to 3. Now the thing that I forgot to do is the step is hitting at 1 second. So if I double click the step, it says step time is 1. It's going to start at 1 second. So I'm going to set it to 0. Okay, and then we'll run it again. And there we go. Auto scale it. Okay, and so it's just like I said, it's 1/2 second time constant, and so within 2 seconds it's settled to within about 2% of the final value. So I've basically captured everything by simulating for 6 time constants here. So now let's make this a closed loop system. So I go over here to the Simulink browser. I think it's in signal routing. It's in math operations. So I'm going to add a, these are not my favorite ones here. Let's look in commonly used blocks. Taking a little bit of hunting. Here's a summing block, okay? So I'm going to get rid this line, and this line, and my transfer function. And I'm going to add a gain here, okay? So it's like our closed loop system. And I'm going to enter in for the value of the gain. I'm going to make it called K, just like I used in some of the lecture notes. Okay, so there it is. I'll go ahead and do view. I'm going to fit it to the window, make it a little bit bigger. So it's more easy to see what's going on here. View, put selection to view. Oh, didn't mean to do that. View, system to view. Okay, there we go. And it's a little bit big now, but I can move some things around. So I've got my summing junction here. Everything here. Select everything, move it up. Okay, there we go. And I'm using this to make a feedback loop. So I've got connecting there, connecting there, connecting here. I'm going to connect this guy as the feedback loop. I'm just changing it so it's negative feedback, list of signs. So I changed the last sign here to be negative. Okay, and so now I have a negative feedback loop that looks kind of like the block diagrams that I would draw in lecture. Be really careful. I'll just leave it as it is. Okay, and now K is not defined. I got to go up to my command window here. I'm going to set K is equal to 1. Okay, and if you remember from lecture, what happens is that I'm going to get a closed loop pole. The open loop pole is at -2. Now the closed loop pole is going to be at minus the quantity 2 plus k. Okay, so since k is 1, that means 2 plus k is 3. Okay, so the closed loop time constant should now be 1/3, 1 over 3. Okay, so let's run it. Let's see what it does. So I go over here to my scope block, auto scale it, and well, maybe it's not so opposite. So in 1/3 of a second is the time constant. So 4 time constant is about 1.2 seconds, and so it's obviously faster than it was. Maybe it's not incredibly fast compared to what we started out with. Let's make it so that the time constant is 10, or 1/10 of a second. Okay, 1/10 of a second will be really fast. So to do that, I start out. I know that my pole. I want my pole to be at -10. So I'm going to set k equals 8 here. Okay, because 8 plus 2 is 10. And run it again. Okay, and so now the time constant is 1/10 of a second, and so 4 time constants is 0.4, and so that would be right up to here. Okay, so you see that the system is getting faster and faster, right? In the beginning, we sort of had an exponential rise where it was kind of taking a couple of seconds to get settled, and now it's much faster. So if we think about this system as being, if we were doing a thermal control system, this is something where it really is when we remember the step is basically our reference input. We want it to go. We want the output here to match the step, and so the speed with which the output goes to to match the step is really important, and you see it's getting much faster. And we could increase k how we like to make it even faster. The other thing we might want to do is the error here. This output of this summing junction is the error, and so we could put another scope on that. Let me move this, and we can look at how the error signal goes to 0. It won't go to 0, but it's going to go to a small value, and it turns out what will happen is that the bigger I make the gain, the smaller that error will be. Remember, this is basically like a proportional control system here. Let's run it. I'm going to double click on this scope here, and so the scope here, this scope 1 is, I could call it, I can actually give it a name here, I can call it error. Oops. Let's say this is like, we're imagining it's temperature, right? So we could call this temperature. And now, so that changed the block here. So it says temp here on the display, and it says error here. I'll make these a little bit bigger. Oops, I didn't make it that big. Anyway, there it is. So you see what happens is that the error starts out at 1 and it goes down to 0.2. And in fact, if I make the gain larger, so if I come over to here and I make k equal 50, and we can run it again. And now the response is really fast. And if you look at that, what happens is that this is the error signal here. The error signal starts out as soon as we change the set point here. Our set point here is the step. We're setting that to 1. And so the error is initially 1, and it gets driven down to 0.05. So the error between the desired set point, so I can even change that, like this is the temperature set point. Instead of calling it step, I call it set point, like that. So the error is the difference between the set point and the actual temperature of my system, and so I've made it very small. Okay. That's all that I wanted to show. This gives you an idea about how to use Simulink, and hopefully you'll find it useful.